Can everybody can everybody hear up there? We're good? All right. So last time we talked about order statistics, which generally means finding not just the minimum, the maximum, but the ith largest in general. It's kind of a sub-problem of sorting, because if you can sort, you can find all of them for every I, the ith largest. And we said it's a simple lower bound of linear, and you have to look at every item, otherwise you wouldn't know that's a Google somewhere hiding or minus a Google, and so you have to look at every item. That's a lower bound that no algorithm can do it less than linear time. And we gave linear time algorithm to find the min or the max. We said that n-1 comparisons are sufficient by this algorithm, very simple two-line algorithm. And together with the fact that linear time is necessary, it means that algorithm was optimal. And then we showed n/2 comparisons are necessary. That wasn't easy to show. We had to use kind of a knowledge-based proof, what is known by any algorithm that runs a minimum finding scheme of whatever kind whatsoever. And we said that n/2 comparisons are n-1 comparisons are also necessary, not just sufficient. So that's a sharp bound. The upper bound, lower bound meet at n-1. To find the min and the max, you can easily do it by finding them separately, but that loses a lot of information. So you can be more clever and cache some of the work, some of the results of the comparisons, and then use that to your advantage. And that reduces the total number of comparisons to find the min and the max to 3/2 n. That's a 25% improvement. And that's also necessary. The proof wasn't easy. It's a lower bound proof, more complicated than the one for just finding the min or the max separately. You track the knowledge, you see how much information is gained at every step of any possible algorithm. Bottom line is that 3/2 n minus 2 are also necessary, not just sufficient. So that algorithm was optimal in terms of the number, the total number of comparisons, not just asymptotically, but the exact number. Okay, that's a good day when you can prove results like that. We found the min and we found the max and the next to max using kind of a tournament-style argument. If a bunch of sports people are competing, the best player can win against everybody, but the next to the best player can lose only to the best player, not to anybody else. Once you realize that, you can track the remaining logarithmic number of players that these next to maximum lost to, that the maximum lost to, and one of them will be the next to max. And that's a way of doing it. And you can also prove the n-2 plus log n lower bound separately. We haven't done it. It's a little bit tricky, so we'll skip over that. But for extra credit, try to prove that too. And then we talked about selection in general, the ith largest. And we said that if you can find the median in linear time, that suffices to find any ith largest, not just the median, which is the n/2 largest, also in linear time, by repeated calls to the median. So if you're trying to find the median of 100 things, and you can do it in linear time, you can find any ith. For example, if you try to find the 87th largest of 100 things, find the median first, then look at only things larger than the median. And you can partition that into two sets, larger and smaller than the median, in linear time. And then from the upper 50, to find the 87th largest of the original, you need to find the 37th largest from the upper 50. That's equivalent to the first goal. And then you keep going. So you do a linear amount of work at every step. You divide the space of input items by half at every stage. That's divide and conquer. And you're not touching the other items any further. You're not recursing on the other half, just the half that you're interested in. You're converging on the 87th largest. And you do this logarithmic number of times, and the space gets smaller and smaller and smaller in terms of how many items you're dealing with. And it all converges to roughly 2n, and that's linear. But that's all contained. So how many understand that schema? Okay, because now the remaining hurdle is to find the actual median in linear time. And that's what we'll try to do today. That'll be the most subtle algorithm we've seen to date, actually, in this class. And we'll see ones that are even more subtle than that. if you just want to find the median in any old time and you don't care about efficiency, obviously you can do it in n log n time because you can just sort and look in the middle and there's the median. But obviously we're going to try to do better than that. Okay. So we're going to first do it kind of probabilistically, and it'll be average case linear, but worst case not linear. And then we'll see how we can make the worst case also linear, not just the average case. So the algorithm we're about to look at, we're going to call it quick select because it's modeled after quick sort. So basically, you partition around some pivot. You pick a pivot, just like in quick sort. You pick some arbitrary item, and you put everything smaller than that item to its left and everything larger than that item to its right in the array. And you can do that in linear time, obviously. You just have to touch every item just once to do this partition around some pivot. Which pivot? Let's say some arbitrary pivot. Doesn't matter what, like the first thing in the array. Okay. And let's say that was the pivot, Q. And everything to the left of it now is smaller than it. Everything to the right of it is now larger than it. Okay. So we partition into two pieces. Now, just like quicksort, these two pieces don't have to be even. They don't have to be half and half. It could be 60-40 or even 90-10 or even 99-1 in terms of percentage. Okay, but on average, they'll be more or less equal if the numbers are randomized and you're selecting pivots at random. So let's say the index of this pivot is k. Okay, so the array goes from P to R. I deliberately don't do it from 1 to n because we're going to have to recurse on these pieces. So at the beginning, P is 1 and R is n. But later, as we recurse on smaller or arbitrary pieces of the array, P and R will be different values. So k is the index of this pivot in the array. So it's the index, the number of elements here is, excuse me, Q is the index of this pivot. The number of elements to the left of Q is Q minus P plus 1 elements in this portion. And in this portion, you have R minus Q elements over here. So I'm just kind of representing them as quantities. So we know how many there are kind of parametrically. So if I is less than k, in other words, the ith largest that we're trying to find falls in this bunch as opposed to in this bunch, we're going to then do quick select the ith largest in this portion. Okay. But if I is greater than k, in other words, the ith that we're trying to select is falling in this portion, in other words, I is greater than k, I is greater than the number of elements here in this first portion, then we're going to do a quick select recurse on the second half. Okay. And when we recurse on the second half, we're not going for the ith largest anymore. We're going to try to find the I minus kth largest because there's k of them here, and we're not even looking at any of them. So whatever the ith largest overall was, it's the I minus kth largest in this upper portion. How many understand that? Just like we did on a previous slide. Okay. When we had 100, and we're going for the 87th largest. So that's the 37th largest in the upper 50, which is the 87th largest in the whole 100, 1 to 100. Okay, but keep in mind that we're only recursing on one group or the other, but not both. In quicksort, we recurse on both pieces because we have to. We need to sort the whole thing. But here, we're quickly converging on the piece that has the ith largest and ignoring the other piece. So we only recurse on the one that actually contains the thing that we want, the ith largest, but not the other piece. We don't recurse on the other one. So the algorithm is pretty much that. Here it's a pseudocode. So I'm selecting in the array X in the range P in green through R. That's the end of the portion of the array in which we're doing the selection. And if P is equal to R, then we just return that element, right? If the array is just one element large, the median of an array with just one thing in it is that thing. Trivially, that's the base of the recursion, so that's the easy part. And then we partition the array from P to R, and Q is this element that we're partitioning on. Okay, it's the index of that element more precisely. And K is the number of things in that range. So K here in this pseudocode is exactly this K that we talked about. It's the number of things in the lower portion of the split. Okay, so now the partition just splits the array around this pivot element. Which pivot element? The one that we picked randomly. Doesn't matter which one at each case. And here's that two cases. If I is less than K, we're looking for the ith largest, and there's K elements here, and K is bigger than I. That means the ith largest we're looking for is in the first portion of the array. So we recurse on the first portion. We recurse on the array X from P to Q, and we're looking for the ith largest. Otherwise, we recurse on the upper portion of the array, which is this portion here that contains R minus Q elements. So we recurse from the element Q plus 1, which is the first element of the upper portion, to the end of the upper portion, which is element R over here. And we're not looking for the ith anymore. We're looking for the ith minus kth largest in the upper portion, just like we were saying over here. So that's the pseudocode that reflects the logic of this approach up here. How many understand this algorithm? Okay, this will eventually give you the ith largest through this recursive process. Now, why is the time O of n on average? The analysis is very similar to that of quicksort, except with quicksort you recurse on both halves, both portions of this. I shouldn't say halves because that implies that they're equal. They're not necessarily equal, so it's two portions, one portion and the other portion. In quicksort, we recurse on both portions separately. In quick select, this algorithm, we only recurse on one or the other, but not both. And so on average, the portion size keeps decreasing exponentially by a factor roughly of 2 every time, and that converges. The total amount of work converges to linear. At first iteration, you'll do about n amount of work, then n over 2, then n over 4, then n over 8 in successive lower levels of the recursion, and that will all add up to linear on average. This is kind of an average analysis. Yeah?
I don't think I get the algorithm. Like, why does it work on unsorted lists?
Ah, so why does it work on unsorted lists? Why did this work on an unsorted list? First, everything is unsorted, and we somehow magically found the median in linear time, and there it is at the middle. What you do next, just like in quicksort, you partition around this pivot, the pivot being the median. So you put everything less than the median to the left of the median. You put everything larger than the median to the right of the median. In other words, you separate the array into smaller things and larger things than the median. And then you recurse on the right portion. Okay, but that's a very good question. So here it's exactly the same thing. Once you select a pivot element, this partition rearranges the array so that everything less than the pivot is to its left, and everything larger than the pivot is to its right. So with respect to the pivot, the array is kind of pseudo-sorted. It's not completely sorted, but it's sorted with respect to the pivot. Everything to the left of the pivot is smaller than the pivot element, and everything to the right of the pivot is larger than the pivot element. That's the pseudo-order that the partition function that we're calling right here, the random partition, gives us back. It rearranges the array. But the point is, it's not sorting the entire array, it just rearranges it to preserve that property with respect to the pivot. Okay. Notice that when all this is done, the array won't be sorted at the end. It'll be a little more sorted than before, but not completely sorted. How many can see that? Yeah, because things smaller than a pivot will be moving to its left, things larger than a pivot will be moving to its right, and there's some pseudo-sorting going on here. Things are kind of migrating in the right direction as if it was sorted, but it's not going to completely sort the array. Because if it completely sorted the array, it's not going to happen in linear time. We already know that, because n log n is a lower bound for sorting. So there's nothing magical happening here that breaks the lower bound for sorting. And intuitively, you can sort of see why this does some sorting, right? Because you're doing only half the work of quicksort at every step. You're recursing on either the left or the right portion, but not the other. So you're leaving some things unsorted, but you're sorting other things, and you keep going. And where you end up depends on what the data looks like. But so it's like a pseudo sort that doesn't quite complete the sort, but at the end you'll know what the ith largest is. And that also reinforces the intuition that to find the ith largest, you don't necessarily need to sort. Sorting finds the first largest, the second largest, the third largest, the fourth largest, the 50th largest, the 100th largest, and the nth largest, all of them. Sort does all that work. How many get that? But you only want one of them, not all, and not any of the others. So selection, ith selection, is kind of a weaker operation than sorting, because you only want a small portion of the total amount of work that sorting actually gives you, and you don't need the rest. So why should you spend all that time for things you don't need? Don't buy what you don't want or don't need. Right? So this scheme helps avoid complete sorting. And that's how it kind of makes an end run around the lower bound for sorting if you just want the ith largest and not any of the others. Okay, any questions about this? Because now we're going to get into a much more complicated algorithm that avoids this quadratic worst case behavior. And by the way, I just said it, but why is it true? Why is the behavior of this, even though on average it's linear time, in the worst case it's terrible. It's quadratic. N squared.
So we have put all the elements as smaller than the pivot to the left. So why the ith largest is on the left?
Yeah. So just like in quicksort, it suffers from the same worst case behavior as quicksort, because just like in quicksort, if you pick a bad pivot, the split won't be 50-50 or 60-40 or 70-30. It'll be 99 and 1 or 999 and 1. It'll be terribly skewed. And you keep getting you'll keep recursing on the huge portion, not on a tiny portion that's the other portion. And so and then you have to do a linear amount of work at every stage. So it's linear plus linear plus linear plus linear, a linear amount of times. And so linear times linear is quadratic, just like quicksort, same problem. Yeah.
So you're randomly selecting a pivot point, and then but that pivot point will move. Say there are many more values that need to be, say, to the left of it than there are spaces before that pivot point will move.
Yeah. So when you pick a pivot, the pivot itself is not necessarily at the place where it will end up after you rearrange things. So you can pick an arbitrary pivot and then rearrange the array so one way to do it is take a second array, initialize it to all zeros. Look at the pivot, go through every element in the original array, everything that's smaller than the pivot, put it in the second array. Then put the pivot next. Then put everything scan the array again, everything larger than the pivot, then keep putting it after the pivot, and then the second array replaces the first. So, of course, you don't have to use a second array. You can do it in situ by being a little more clever. I'll leave it up to you to see how you can do it without using a second array. But the second array doesn't change the time complexity or the space complexity. It just doubles the array, by 2. But that's an easy way to see how the pivot ends up some arbitrary place, not where it started from, depending on how many items are less than it, how many items are larger than it. Just like in quicksort. Quicksort does the same thing, actually.
So if the elements on either side of that pivot aren't sorted, then going back to the previous algorithm, why would the 87th largest be the 37th largest on that?
Oh, okay. Another good question. So the previous slides said, so assume this is not the median. This is just the pivot. If the pivot is a median, you're good because it's half and half. But let's say it's the pivot. So everything to the left of it, right here, is smaller than the pivot. So all this stuff here is smaller than the pivot. All this stuff here is larger than the pivot. And the pivot is sitting somewhere, and in this case, it's sitting at the 50th place if you go from 1 to 100 in the array. And you're looking for the 87th, in this example, I guess, or the previous example. You're looking for the 87th in this entire array. And everything from this point downwards is smaller than the median. And the median is in the 50th place. So obviously the 87th largest is not going to be anywhere in this portion right here, because that's 50 of them, and you're looking for the 87th. So it's got to be in this portion. And where in this portion is going to be, there's 50 of them here, well, 87 is going to be in the 37th place in this upper 50, because together with this lower 50, 50 plus 37 is 87, which is the one we're looking for. So that's kind of the logic there. Any more questions about that? It's good that we're asking questions, because the next algorithm we'll see will be a lot more complicated than this. It'll probably take us to, the rest of the hour to go through it. Yeah. The average case? So how do you calculate the average case? So the argument we gave is intuitive. We said on average it'll be roughly half and half. In each case it'll roughly be half and half again. So roughly half plus roughly a quarter plus roughly an eighth is all roughly n. But you're right. That's not a rigorous argument. It's an intuition. If you really want to prove it rigorously, you got to do some more heavy lifting than that, using probabilities. And for extra credit, and even look it up. So, that's okay too, and understand and explain that to me for extra credit. But you're right; it has to be nailed down rigorously mathematically. But the intuition is correct, and the mathematical version that's rigorous basically capitulates this intuitive explanation more precisely with probabilities, basically. And by the way, whenever you talk about probabilities, you have to worry about the underlying distribution of the probability. This random variable of, you have to worry about the distribution, where it's coming from. Is it uniform? Is it Poisson? Is it normal distribution? Is it some weird distribution that's skewed? And so in all these analyses, we typically assume that all permutations are equally probable. It's kind of uniform distribution across all the permutations. No permutation is more likely than any other permutation, and it's n factorial of them. But any kind of probabilistic analysis needs to consider which distribution we're drawing things from, right? I mean, if you're flipping heads and tails, you're assuming that heads are equally likely to tails. It's 50-50. But if it was 90-10, you can expect a lot more heads than tails. And when you start talking about, what's the average number of runs of the same head or tail kind of sequence, and that depends on the distribution, obviously. So I'm just a simple example illustrating what I just said. Okay. Now, why is this quadratic? Again, we said if we pick very skewed portions, then you'll do a lot of work over and over and over again, linear amount of work at every iteration. It'll be a linear amount of iterations. It wouldn't end up after a logarithmic number of splits. The number of splits will be a lot bigger than logarithmic and possibly linear. You're doing a linear amount of work at every split, so it's total n squared. Okay, so far so good? All right, so let's see how deeply you understand this one before we even go further. What if we wanted to make the worst case time not n squared? N squared is pretty bad. Quadratic is usually terrible. Squaring 1,000 is only 1,000,000. Squaring 1,000,000 is only 1,000,000,000,000. I mean, 1,000,000,000 is not small, but in a few minutes your processor can count to 1,000,000,000,000. But squaring 1,000,000,000, you won't be able to do on your computer. If you try to count to a billion squared, that will take weeks or months. If you try to square 1,000,000,000,000, it won't end in your lifetime. So squaring is not great. You should avoid it whenever possible. So how do you reduce the worst case time of this algorithm to something less than quadratic?
Could you run a sorting algorithm?
Yeah. The force is strong in this one. Yeah, you run a sorting algorithm in parallel. And if this goes quadratic, well, the sorting will end in n log n time. Then abort this when the sort ends, and where is your ith largest? The sort will give you all of them. Just go to the ith largest in the sorted array, and then you'll know. And this will work in n log n time. So that's a easy way to cap the quadratic at n log n. And keep that in mind when you design algorithms and systems, You're not bound to worst case scenarios just because they're there. Yeah, this has a worst case scenario of that, but not if you run it in parallel with something else, or with other things. In fact, what's another way to reduce the worst? Well, what's another way to ensure that the average case doesn't degrade to a worst case without doing this trick? What else could you do that without even running two things in parallel? Think what we did in quicksort to get this to happen. Randomize. Now you're getting it. I'm proud of you. So when you get the original array, before you even find the ith largest, randomize it first. Then the behavior of this will be very fast, because it'd be hard to find bad pivots if it's all random, on average, statistically speaking. Or there's other tricks you can do.
Multiple pivots in parallel.
Yeah, pick one pivot, do the partition. See how you like that partition. Is it 60-40? Is it 70-30? Or is it 99-1? If you don't like that partition, what should you do? Pick another partition. Pick another pivot, repartition, and then see if you like that better. So pick 3 pivots or 5 pivots separately, partition, 3 or 5 different times. Take the best one in terms of skewness, equal sizeness of the partition, as close to 50-50 as you can. Then recurse with that. Forget the other 4. How many understand that? So even if even if things are bad on one pivot, maybe they'll be good on a second or third or fourth try. I mean, it'd be hard for it to be bad on all 5 tries, right? I mean, if you throw a dice, if you flip a coin once, it may come out heads, and you need a tail, and the second time, may be bad too. But if you flip it 5 times, 6 times, I mean, the chances are smaller and smaller that you wouldn't see the tail that you expect to see. It's like Russian roulette, right? I mean, you may survive 1 round, but you won't survive 5. Certainly, you won't survive 20 rounds, assuming 6 rounds in a chamber. Anyway, but that's a dark example, but you get the idea, right? I mean, you work the numbers. There's other things in life that are like that, right? When you get a ticket for speeding, right? You may feel bad, and you may say it's unfair, and all these people got away without a ticket, and you're the one who got. Well, not exactly. That's not the only time you sped, did you? You can get away with speeding once, and nothing will happen. A policeman just won't happen to be there at that time, at that place, when you did something illegal with your car, like speeding or bad parking or whatever. You do it a second time, a third time. Eventually, it'll catch up. The probabilities will add up, and eventually you'll be caught. And when you get a speeding ticket, it's not because you sped once. It's because you sped probably 50 or 100 times over a period of 6 months, and finally, the odds were not in your favor. Eventually. May the odds be ever in your favor. Who said that? So if you think rationally, when you get when you speed, it doesn't cost you $100 to break the speed limit. It only costs you about 50 cents, because you'll only be caught once in 200 times, and the speeding ticket, yeah, it'll be $100 for that once. But if you amortize it over all the other times that you spent, you're getting a really good deal. You're speeding and you're only paying 50 cents a pop, right? Same for parking, right? You can actually use this kind of statistics and probabilistic reasoning to get a really good deal on parking. Let me explain. Just park anywhere you want. Park illegally. Assuming that they're not too aggressive in like constantly giving tickets 24/7. You'll get away with it if you just want to park for a few minutes or half an hour. Chances are you won't get caught, right? The parking attendant is not going to be everywhere writing tickets all the time. Just in one place or another place, and they're walking around. Chances are you'll get back to your car. You'll be fine. So if you do this, 50 times, you may get only a ticket once, and that ticket may be $50, and that's a lot for one ticket. But if you amortize that over the 50 times you parked for free illegally, you're only paying $1 to park each time. on average. And that could be a lot cheaper than actually paying $5, for the actual permit to park there once every time. Anyway, I'm not saying you should break the law. That's not what I'm saying. Don't go around and say, "Oh, Professor Robin told you shouldn't pay for parking." No, but you have to kind of keep probabilistics and statistical reasoning as you go through life, right? I can give you a lot of other scenarios from real life. Eventually, the odds catch up with you. That's the thing, right? The old saying, "Crime doesn't pay." It's not completely true. Not every time. Sometimes it pays, and occasionally, when it catches up with you, you get charged for all these other times, and that's when it doesn't really pay. But again, I'm not saying you should break the law and do nasty things or illegal things, but statistically, that's how things go. Okay. All right. So now, here's the big one. Now we're going to make the worst case linear time, and that is a big hurdle. That algorithm was not discovered for decades, and people were looking for it. For decades, nobody knew how to do median selection in linear time. And remember, if you can do median selection, you can find the ith largest too, because you can just keep repeating the median, and you're doing partitioning by half. So if quick select found the median at every time, it would work in linear time. How many remember that from 3 slides ago? Just 3 people? Okay, because if you don't, I'm not sure you'll fully appreciate the value of what we're about to see. So let me go back. I want to see more hands next time I ask it in 60 seconds. So we're saying that if you can find the median in linear time, then you can do quick select. You can partition it evenly into half and half, and then recurse on the right one, and then you can find the ith largest for any I, not just the median, which is the n over 2i, ith largest. That's what the median is, n over 2 ith largest. So if you can find the median repeatedly, just keep going, and all that will converge to linear time. So the holy grail of order statistics would be to find the median in linear time, and then you get all of them in linear time for any I. How many get that? Okay, it's important, because that's why we're so aggressively going after the median in linear time. That's why it was such an important problem. And for decades, nobody knew how to do this. Until 5 guys, Bloom, Floyd, Pratt, Reversed, and Tarjan, and most of them were Turing Award winners, and one of them, Rivest, was the R in RSA. That's how smart these guys were. It took 5 of them to come up with the following algorithm, which we're about to see. Yeah.
The last problem, when we say if we find the median every time, why is it still linear and not log n?
Fair question. If you find the median in linear time, why is it converged to linear, not to n log n?
Just log n, not even n log n.
Or log n? Because every time you recurse on the half, to do the partition, you got to touch everything in that half to rearrange it around the pivot. Because yeah, you found the median, but that doesn't give you the partition. You still have to put everything less than it to its left, everything to the right of it to its right, and then recurse on that half. And so you're doing a linear amount of time at every iteration. Linear in the size of this smaller and smaller and smaller partitions. So first you're doing n work, then n over 2 work, then n over 4, then n over 8, and all that converges to linear, not to log. There's a log number of them, but the total amount of work is linear. Okay, so these 5 guys finally got together, and after decades of research, here's how it's going to work. So now we're going to describe the algorithm like pictorially, because it's easier that way, otherwise it won't even make sense. All right, so here are all the items that we're trying to find the median of in linear time. And we're going to arrange them arbitrarily as n over 5 groups of 5 each. You'll see in a couple of minutes, or maybe in 10 minutes, why we're doing it this way, why we're partitioning it into n over 5 groups of 5 each. But there are all the n items that we're trying to find the median of, okay, diagrammatically. After we do this, we sort each group high to low this way. So this guy is higher than this guy, is higher than this guy, is higher than this guy, is higher than that guy. So we sort each group of 5 individually within that group. Not sorting the entire thing, we're just sorting every group of 5. All right, so we impose this order like that. And by the way, we're assuming all the items are unique without loss of generality. Why is it without loss of generality that we're assuming they're unique? Why aren't we losing generality? Again, this is an old question that we harped on several times before. Why is it a safe assumption to say, okay, they're all unique? Disambiguate non-unique things by the index of the array. Excellent. Now you're getting it. You see the same tricks come up again and again. Now you compute the median of all the medians of each group. So each group, the median of the 5 will be in the middle. Why? Because they're ascending order. The median of the second group will be this third guy in the middle, and so on. So this row will contain the medians of each group. And you find now this guy, which is the median of all these medians. So we recurse. Which algorithm do we use to recurse to find the median of this group of blue ones? Which algorithm? This one. The very algorithm we're still describing. We're calling it recursively on this group in the middle of all the medians. And there's n over 5 of these medians. Right? There's n over 5 in each row, and there's 5 rows, so n over 5 times 5 is n, so it's n total, and each row contains n over 5, and each column contains just 5. So we recurse on all of these medians of each group, respectively, together, and find the median of all of those. You'll see in a minute why we're doing that. But now we're just doing that. In a minute you'll see why. So now we're going to rearrange the columns in a way that partitions these columns around that red median. So move all the columns that have a smaller median than the red to its left, and move every column that has a larger median than the median of the medians, move them to the right of the middle. So all these columns now have been rearranged so that all of these blue medians here to the left of this red are less than it, and all of these medians to the right of this red are larger than it. So you partition these rows around that red median of medians. How many understand that step? Okay. Oh, God, I'll take it. It's about half the class. All right. We're not done yet. We're halfway there. Any questions so far? Or we can come back to it after we see the rest of the algorithm. So the rest of the algorithm is this. We see that because all of these guys here are larger than the red, and all of these guys up here are larger than their respective blues because they're all sorted downwards, everything in the green box is larger than the red. How many can see that? By transitivity. Okay. Similarly, everything in this lower box here in green is smaller than the red by the exact same reason, by transitivity, because the red is the larger of all of these blues, and all these are smaller than all of these blues, so all these are smaller than this red. And that's three-tenths of the elements are in this box, and 3/10 are in this box. How many can see that? Roughly 30%, and not even roughly, but exactly 30%, plus or minus epsilon. So there's a big chunk of them right here and a big chunk of them up there. Now what do you do? Partition all the elements around the median of the medians, which is the red element. It's color-coded here. This is like the median of the medians, but we could call it the red element. Partition the entire set, all n things, around that red element. Take everything smaller than that red element, put it to the left of the red element in the original array, or you can use a secondary array if you want, it's equivalent, and put everything larger than this median of medians to the right of that median of medians in this new array. And now you're basically doing what quick select did a couple of slides ago. You recurse on either the lower or the upper half. How many see where this is going? Okay, a few people. We're not quite finished yet, but we're getting there. And then recurse this original entire high-level algorithm on either the lower or the upper part of this partition around the median of medians. And keep doing that, just like you did in quick select a couple of slides ago. So this work here is almost the same as quick select. You partition around the pivot, and then you see where the pivot ends, and there'll be a lower half and an upper half, and then you see where the median belongs in the lower half or the upper half, and then you recurse on that half but not the other. I shouldn't say half. You recurse on that portion and not the other portion, because they may not be halves, they may not be equal, because you're just partitioning around the pivot. Except in this algorithm, you partition around a special pivot, this red pivot. That's the median of all the medians of all the groups of 5. How many see that this is correct? Never mind how fast it runs. How many see that this will work? Okay, just a few people see that this even works. Okay. Let's just first establish that it works, because if you don't see it works, there's no point discussing how fast it works, right? Obviously. Right. I mean, if there's a pair of shoes that you don't like, and then you'll never wear, and you'll never buy, you don't need to know how much they cost, obviously, right? Because it's a moot point. So let's see that this works. Then we'll talk about the time complexity. This whole process that we did, beginning by partitioning into groups of 5, and then taking the median of every group, and then taking the median of all the medians, and then on and on and on, we ended up selecting this red dot. Never mind how we selected it. We ended up selecting it, and that's the pivot now. The red dot is the pivot. And now we're doing quick select from 2 slides ago. How many can see that that works? Oh, good. So I'm glad I explained it that way. Once you select a pivot, it doesn't matter how you select it. And then you partition around the pivot, and then you recurse on this half, this portion or that portion, and you keep going. Doesn't matter how you select the pivot. Eventually, you'll find the ith large. It's just like quick select did a couple slides ago. It works. It's correct. But here's the twist. Picking the pivot this way makes the partition not too skewed, but rather more even. And that's when you begin to save a lot of time. This one can never go quadratic now. Why? Because when you pick this pivot, you already told me that you can see that 30% of the items are less than this pivot, and 30% of the items are greater than this red pivot. So if that's the pivot you decide to pick, the partition cannot be worse than 70-30. How many can see that? Yeah. It's not going to be 20-80 or 90-10 partition. Why? Because both portions of the partition must contain 30% each of the total elements. And that's why we picked this pivot in this complicated way. Okay, how many are beginning to see now what's going on? Oh, good. Any questions so far? We're not done with the analysis yet, except to say that this way of picking a pivot is more fair in terms of the skewness of the partition. It will never be 90-10 or even 80-20. It'll be 70-30 or better in terms of evenness. Yeah. Why is it 70? Because there's 30%, 3/10 of the items are less than this red right here. And 30%, 3/10 of them are larger than it. So when we pick it and then partition the others around it, 30% must be below it, 30% must be above it, and the rest may fall wherever they like. But it doesn't matter where they fall. And this guarantees that 30% are less than it, 30% are greater than it, so it'll never be worse than 30-70. Because if it was 90-10, if it was 90% to 10%, that 10% can contain 30%, because it's only 10%. So the smaller portion of the partition must be at least 3/10 of the total. And the higher portion must still be also at least 3/10 of the total, which means that the partition cannot be too skewed. It cannot fall lower than 30% of the bottom or higher than 30% of the top. It's got to be somewhere between them. Does that make sense? you have to kind of meditate over it to see how it all fits together. There's a question? Yeah. Yes. Yeah. 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 So notice what's going on here in terms of recursion. First, you find the median of every group. That part is easy. You don't need to recurse on that. Why? Why is it easy to find the median of each group of 5? Constant time. There's only 5 of them, so you use bubble sort to sort the 5, and then the middle one will be the median of the 5, and that's constant time because 5 squared is still constant, and you don't have to worry about it. So there's lots of ways to find. So that's the easy part. And then you take this middle fifth. You take this middle row of n over 5, all the blue ones, and you call yourself recursively using the original high-level algorithm to find the median of those, which is the red dot. That's one recursion. There's a second recursion that's different than the first. When you find this median, you then partition all the elements around the median, and you end up with a partition, and then you recurse a second different time on either the lower or the upper portion of the partition around the red dot. And that recursion is different than the first recursion. It still uses the high-level algorithm all over again. So that very same high-level algorithm is using it in this quick select type mode of recursion, but it's a different phase of the algorithm than the first. So there's 2 different recursions going on. Recursion 1 and recursion 2. How many can see that? Right? So you recurse once just to find the median of the medians. And once you have that, you rearrange and recurse a second time on the upper or the lower portion of the partition, resulting from partitioning it around the median of the median. So it's two different modalities of recursion going on here, and both of them use the exact same high-level algorithm for each one of those 2. There's a lot of recursion going on here, more so than algorithm we've seen so far. In quicksort, you recurse twice, but they're exactly the same type of recursion, and they're kind of parallel to each other. Here, the 2 recursions are kind of off kilter off each other. One is the first recursion just finds the pivot to define the second recursion. It's not like quicksort. It's not like merge sort, where the 2 halves are completely symmetric. The 2 halves of the recursion are completely symmetric logically and time-wise and algorithmically. Here, they accomplish 2 different things at 2 different times for 2 different reasons. Yeah.
Curious, did the authors explore groups of 7 or groups of 3?
Yeah, we'll get to that. Let's not muddy the water yet because it's still not clear yet. We're not finished with the analysis. But that's a very good insight. What if you use groups of 7, yes, or groups of 9, or groups of 3 instead of 5 even? We'll get to that in a second. That's good. That's a very good question. It means you're really beginning to wrap your mind around these concepts. Any other questions so far? Because we haven't done the time analysis yet. All we've done is create this complicated ways of finding the partition element in red, and essentially then followed the same template as quick select. But we're doing double recursion here. We're recursing this way and that way at every level, and then keep doing that at every sub-level. That's a heck of a lot of recursion going on. And how can all those recursive calls still add up to linear time? I mean, maybe it's even worse than quadratic. There's so much recursion going on here. We're about to analyze it. Yeah. We don't know where it is, actually. We're not saying that the median of the entire group is only in this green or only in this green. We don't know that. It could be somewhere else. You're right. But what we're doing is saying, once you pick the pivot this way, it guarantees that at least 30% of the items are larger than it, and at least 30% of the items are smaller than it. And knowing that allows us to completely repartition it, completely ignoring that, repartition everything around the red into 2 groups, just like quick select, and then they recurse either on the lower or the upper but we already know from this analysis that at least 30% of the items will be in either group. So the recursion won't be too skewed. It'll never be worse than 70-30. Yes, exactly. So because we're eliminating at least 30% of the items at every step, we can't iterate for too long before we reach the bottom. In fact, logarithmic number of times. That's a good insight, and that's exactly why we do this. So all this complexity and trickery was just basically designed to accomplish a more even split. And by more even, we don't mean 50-50, but no worse than 70-30. And then once you keep doing that, you eliminate a constant fraction at least at every iteration, and then in log steps, logarithmic number of steps, you'll be done with iterating. Yeah. If you divide them into so the recursion just returns the median. So if you call the subroutine with less than 5, or if it's not a multiple of 5, just return the median. And the median is always defined, right? If there's an odd number of things, the median is the middle one. And if there's an even number of things, the median is either this or that. You know, return arbitrarily either this or that. Yeah. 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 Question. Yeah.
Can we make any statements about the top corner of the bottom corner?
Here and here?
Yeah.
Not really, and we don't have to quantify what's happening down here or up here. All we're interested in showing is at least 3/10 of the items are below the red and 3/10 of the items are above the red. And that's all we need to do. We're not sure, you know, it'd be hard to say definite things about what's going on here. Because these are smaller, but then these are larger than it. So these guys, they can be higher than the median, actually. These guys could be lower than the red or higher than, this guy could be a Google right here. And the red could just be 50. Yet it's still sitting over here. Does that make sense? And we don't need to worry about it, because what we're doing next is repartitioning everything around the red from scratch and then recursing on either the lower or the upper portion of that partition. So we don't need to worry about what's happening with the others, and they can be arbitrary values, so you can't say anything about them, and we don't need to. Okay, so I think we're ready for the analysis of how long this takes to run. So recursively, when this runs, the time to run this whole high-level algorithm on n things is the time it takes to run it on n over 5 things, because we call it again on the middle, we call it for the first time on the middle row, that's 1/5 of the things, n over 5. So the time for n is equal to the time for n over 5 plus the time it takes to call it on 7/10 at worst, because 30% will be eliminated or more. So when you call it the second time, it'll only be on 70% or less, because 30% or more will be eliminated. So the time for running it on inputs of size n is the time to run inputs of n over 5 for the first recursion, and 7/10 n for the second recursion, plus to rearrange everything is a linear amount of work. Pick a second array, put everything less than it first, everything greater and then put the pivot in there, then put everything greater than the pivot after the pivot. That's only all a linear amount of work. Okay, so how many see that this is the recurrence relation that represents the you know, in terms of a recurrence relation, recursively, the time it takes to run this algorithm is a function of n. How many can see that? Okay, it's bounded by this expression. And how fast does this go? It's not nice and symmetric like merge sort. Remember merge sort, when we did this way, it's the time. So T of n in merge sort would be T of n over 2 plus T of n over 2 plus O of n. How many remember that? It would both be T of n over 2. Like 2 times T of n over 2. Nice and symmetric. Here the two are very different. T of n over 5 plus T of 7 n over 10 plus linear. Let's see how much that is. First, we'll rewrite the n over 5 as 2n over 10. I just substituted, I just multiplied the numerator and denominator by 2 here to put it over a common denominator so that we can combine them. And when we combine them, we make the, first of all, finding the median is not going to happen in less than linear time. Why? At least linear time to find the median. Because just finding the min or the max already takes linear time. So to find the median is not going to be any cheaper than that. Right? You have to look at every element to find the median. Otherwise, you won't know what it is, just like the min or the max. So the time to find the median is at least a linear function or more than a linear function, grows faster than linear or equal to linear. And whenever you have a function that's super linear, that's linear or more, that's omega of n, this is true. F of x plus y is greater than f of x plus f of y. In fact, when they're equal everywhere, that's almost a definition of linearity. But if it's super linear, adding the two things together, x and y, and then running the function on both, or computing the function on the sum, is always larger, equal to, or larger than the sum of the function computed on each portion of the sum of x plus y. How many kind of believe that or understand that or know that, actually? Yeah. So for example, if you want to square something, if you have two things and you want to square the sum, you're much better off squaring the first, squaring the second, and adding them up. That'll be cheaper. You'll get a smaller quantity than if you add them both up and then square. Why? When you square a sum, what do you get? The square of the first, the square of the second, but there's more. Twice their product is in there too. How many get that? So when you square a sum, you're better off squaring the first and the second, adding them up, and then forget about the rest. You get a discount here. If you just do it that way. The discount is 2xy. That's why this is, and if you cube, you get an even bigger discount, because there's all these other cross terms. Right? And so on and so on. The only time where they're the same is when? When it's a linear function. When the power is 1, not 2 or 3 or 1.5 or anything bigger than 1. Okay, anyway, you can prove this separately in general for any function, not even just polynomials, but that's true in general. So here this function we know is going to end up linear or more. It's a super linear function. Linear or more. So if we invoke the function on x and on y and add the two together, let's invoke it on the sum instead, and that'll be at least as large as that by this reasoning. How many get that? Good. Now you see why I put it over a common denominator, because 2/10 n and 7/10 n is 9/10 n. Here I just added these two here. I didn't do anything else. So this is larger than that by this kind of reasoning. You get a discount. Okay, the rest is the same. So now we have t of n is t of 9/10 n plus linear. And there's the exponential decay. You take 90% and 90% and 90% of that, 90%, and add them all up. It converges to a linear quantity. How many can see that? It's a geometric sum, geometric sequence added up. Just like a half plus a quarter plus an eighth plus a 16th adds up to 1. But it doesn't have to be a half plus a quarter. It could be a third plus 1 over 3 squared plus 1 over 3 cubed. That adds up to less than 1 also. How many understand that? And if you take 90% plus 90% of 90% plus 90% of 90% of 90%, 90% cubed, and you keep adding that up, again it converges to less than 10. Not necessarily 1, but and that's why this t of n is big O of n. Even though there's a heck of a lot of recursion going on here, both the directions. There's recursion to the left, and recursion to the right. Recursion down and sideways, however you want to think about it. There's a lot of recursion. And yet, it all converges to linear, amazingly enough. So now we found the median in big O n, and together with the fact that linear takes omega n to find, this is an optimal algorithm. It's linear to find the median, and we know we can't do better. And this took decades to find, this algorithm. You can see why. It's tricky, it's subtle, it's beautiful, it's elegant. It's not that long, right? If you want to implement this, I mean, you know, a few dozen, 2 or 3 dozen lines of code will accomplish the whole thing. How many can see that? You can implement it in a few dozen lines. It's not even 100 lines. 30, maybe 20, 30 lines if you're thrifty about the code. And this will work in linear time to find the median. And once you do this as a black box subroutine, you can use it to find the ith largest for any I. How would you do that? Just like we did a few slides ago. You'd call this median repeatedly on the upper and lower half, and so you'll recurse on this function, which itself recurses on itself, and that'll be even more recursion. Recursion like 3 different ways. But you'll find the ith largest in linear time using this as a subroutine. Any questions about that? This is not easy. This is the hardest algorithm we've seen so far. We'll see ones that are even more subtle than this and tricky than this. But this is beautiful. This is elegant. This is relatively short. The analysis is a big part of it, why it works so efficiently. And this was the holy grail for decades before these 5 smart guys got together, and a bunch of Turing Awards winners got together and finally knocked this down. This was a big monumental effort. And this now, after it was this was discovered in the 70s, by the way. It's not a new algorithm. After it was discovered, it's used as a black box in many other algorithms. For example, you can use this in quicksort to make quicksort run in worst case n log n time. How? How can this improve quicksort now? Use this to find a partition for quicksort. But quicksort has to use something for partition, then use the median. And now quicksort uses even partitions, and now you can sort much more quickly using quicksort and still enjoy the good average case behavior, and this will bound the worst case. And a whole bunch of other scenarios where you quickly need to find the median of some things, and that helps you to do some higher level operation that uses the median as a black box subroutine. So this is a building block in many other algorithms now. Any questions on this? Yeah?
Well, which process takes the time of t7 times n divided by 2?
Of which one?
The second item.
Here?
Uh-huh.
Because we do the partition and at least 30% are eliminated. So the partition is 70-30 at worst in terms of skewness. It's never 80-20. It's never 90-10. It's 70-30 or better. It could be 60-40. It could be 52-48. So when we call one or the other, you're guaranteed to not have to call it on more than 70% of what you had originally, because 30% will be eliminated. So we're being pessimistic when we say it's t of 7/10 n. It's t of 7/10 n or less. But we're computing an upper bound. So we let it be as skewed as it can possibly be, because we're going to be pessimistic and allow the worst case behavior. So we're going to say t of 7/10, because it can never be worse than 7/10, because 30% will be eliminated, either on the lower or the upper half. Or actually on both halves. 30% are going to be eliminated here, and 30% are going to be eliminated there. Whichever we recurse on, we benefit from this 30% elimination. And we recurse on at most 70% of the remaining ones, or less. But we're computing an upper bound, so we're being pessimistic. And that's why we can say 7/10 here, because it's that or better. And that's still an upper bound. When you compute upper bounds, you can throw away, you can basically be pessimistic. Let's say you want to compute an upper bound on the price of the shopping cart full of groceries. Sometimes you need to do that to see if you have enough cash to buy or whatever, enough in your checking account to write a check. You have a grocery cart, let's say you have 100 things in your grocery cart. What's an easy way to compute an upper bound? Well, you look at it, you say, nothing here costs more than $2. A box of cereal, a banana, an apple, carton of milk. Nothing here costs more than $2. All right, so the upper bound is 100 items times $2 is $200. The $200 is an upper bound for the price of this entire shopping cart. That's an easy way to estimate a quick upper bound on the number of things you buy in the shopping cart. Now, that's overly pessimistic because some things only cost 20 cents, not $2. But if nothing there costs more than $2, you can just multiply the number of things by the $2 and you have a gross quick upper bound. So when you do upper bounds, you can be generous in terms of pessimism, how much things cost and how much they and that's sort of what we're doing here. It can never be worse than 70%. So assume it's always 70%. And if it's less than 70%, it'll be less. But we're computing an upper bound, and that's why we say 70% here. Any other questions? Yeah. Yes. So we're not doing quick select on the blue. We're running the entire algorithm from scratch on only this row.
The worst case is that the worst case will also be quadratic, right? If we are doing quick select on the blue spots.
Oh, I see what you're saying. This blue row contains the medians of each column. Now, the medians of all the columns are not sorted yet. They're not selected yet, or we don't know what the medians, what the median of all the blue ones. It happens to be the red, but how do we know it's the red? By calling this whole subroutine on the entire middle blue row.
She means that when we store the blue rows, the worst case will be
So you're saying that if this is the median of this entire row, this gives you a good partition of that entire row. That much is true. But these other guys, you don't know where they belong. And instead of trying to figure out which ones of these are candidates for the medians and which are not, because some of them could be higher or lower, we don't know. These guys are unrelated to the red dot. These guys are unrelated to the red dot. Some of them here could be larger than the red. Some of them here could be smaller than the red. How many can see that? Outside the green boxes. And we don't know which is which. And instead of worrying about it, partition everything from scratch around the red dot and then recurse using that as the pivot. And then you're okay. You don't have to worry about all these special cases. And you really, in general, can't say anything about these dots that are outside the green boxes and their relation to the median, to the true median, the answer that you're looking for. It could be larger, it could be smaller, you don't know. And they're not sorted, they're random. That's a good question. Now, having said all that, let me just give you a little warning here. This is highly recursive in two different directions. There's going to be overhead here. Yeah, it's linear. It's linear asymptotically. But the constant is very large because of all this recursion and overhead and repartitioning and repivoting and then recursing over and over again, because you're computing medians over and over and over again just to compute that one median that you're really looking for. You're recomputing the median of all sorts of subgroups. How many can see that? Again and again and again, aggressively, recursively, over and over again. And that's going to cost you, yeah, it's all linear time asymptotically, but the constant here is pretty high. How high? High enough so that if you want to find the median of only a few thousand things, don't use this. Just like quicksort. You don't want to sort a 5-card poker hand using quicksort for exactly the same reasons. A lot of overhead and recursion, and, just use bubble sort. So the constant here is large, and it's much larger than quick sort or quick select. The constant could be three digits long, or even 4 digits. Constant could be 1,000 times n, or 5. It depends on how you implement it and how careful you are. So I'm just giving you a caution that just because it's linear time doesn't mean you should always use this to find the median in all scenarios. Okay. same for there's certain kinds of sorting. So it's something that you always need to keep in mind. So you can asymptotic notation hides constants, and that's both a blessing and a curse. It hides constants and allows you to just look at the asymptotics. But if that constants are very large, they're still hidden from you. And you have to be careful of what they really are. If you're not hiding a constant of size Google in the big O of linear. So big O of n sounds good until I tell you, oh, yeah, it's big O of n, but it's a Google times n. Then it's not so good. In fact, it's terrible. Even if it was a million n, it wouldn't be so good. And here's how it works. This is actually a depiction of the selection algorithm in linear time on these items, and the height represents the value of the item, how big each item is. And it just keeps going and going. Now, let me say a few words about the exact upper bounds and lower bounds on these constants. At first, somebody showed that the upper bound is less than 24n. And then somebody showed 5.4n, and so on. So eventually, somebody showed less than 3n, 2.95n, on the exact number of comparisons. This is now exact number of comparisons. This is not the running time. This is the exact number of comparisons absolutely necessary to find the median. So this is separate from the algorithm. This is not to do with the algorithm. This is the theoretical bounds on the number of comparisons. The lower bounds went from 1.5n to 1.7 to 1.8 up to 2. And somewhere between 2n and 3n, roughly, where the minimum number of comparisons it takes to find the median, nobody knows where it is still. It's still an open problem. Each one of these jumps to improve the lower bound by increasing it, or to reduce the upper bound by decreasing it. Each one of those was like a PhD thesis. So you're looking at a bunch of PhD theses right here, or really good papers in theoretical journals and conferences. And there's still a whole lot of room between 3n roughly and 2n. Just again, this is the exact bounds of the number of comparisons. Just like to find the maximum took n minus 1, and to find the min and the max, we already proved it took 3/2 n minus 2. This is the range for median between 2 and 3, 3n and 2n. Okay. Any other questions on any of this? So if not, let's stop here. Next time we'll start talking about computational geometry, which is a really cool topic. And keep coming to the TAs, go to breakout problem solving sessions, and we'll see you next time.
Question regarding the last slide. So we said in the previous slide that the constant here is pretty big, but it seems like it's somewhere between 2 and 3. So is that the constant on the entire algorithm, or just some part of the algorithm?
This constant here is not to do with, it doesn't have anything to do with the algorithm.
Okay.
It's the theoretical bound on how many comparisons are necessary and sufficient,
No matter which
no
algorithm.
matter what algorithm you use.
Oh, okay. So we are saying for that particular algorithm, the constant is pretty big.
Much bigger than this, yeah.
Oh.
In other words, just because it takes n log n comparisons to sort, doesn't mean if you run an algorithm to sort, it will take less than that,
Okay.
or equal to that. For example, bubble sort takes a lot worse than n log n. It still works, it still sorts, but it's a lot worse than this lower bound, than the minimum necessary. So the minimum necessary is within this range.
If someone comes up with an algorithm which is this, which should be better than the previous one.
The algorithm we just shown takes a heck of a lot more than 3n.
So if somebody comes up with around 3n algorithm for the median, that would be an exact number of comparisons.
Oh, if they manage to do the median with an exact number of comparisons, it'll be a lot better than what we just saw, and it'll be a major contribution. Just like sorting or any other problem. If you can do it in less, that's better. But this says that you cannot do it in less than roughly 3n.
Yeah.
no matter how hard you try.
I mean, yeah, but that's still a better number than the
And there's a huge gap between this and the algorithm we just saw.
we just saw.
I mean, the gap is huge. The constant there is in the hundreds or even maybe the thousands, depending how you implement it.
And just one more
yeah.
small question. When we